just look at logarithms and why do we need logarithms. First of all, let us read the definition. We see that the inverse function of the exponential function y equal to a to the x is the function x equal to a to the y. We just swap the x and the y. But we can now write that y there as log of x to the base of a. So if we have log of x to the base of a, we can assume that a to the y is equal to x. In this case, we have restrictions. We have a positive. A must not be 1. It doesn't make sense to have a log of the base 1. And then x is a real number, but only positive numbers, and y can be any real number. Let us zoom in on the graph. On the graph, you will see first of all f, which is just the function y equal to 10 to the x, and here we have the line y equal to x. Then the red graph here, the green graph is now y equal to 10 to the x, and if I mirror that about the line y equal to x, I get the red graph, and that is y equal to log to the base of 10 of x. First of all, if I look here, this is also f of x. You will notice here we have a small f, and this is also h of x. And if I write down the domain of f, which you normally write like this, then we get all real numbers. And if I write down the range of f, I get only r plus. That means the y's are greater than 0. It can't even be equal to 0 because the horizontal axis is also horizontal asymptote for the function f. If I look at the logarithmic function, the red graph, then I see the domain of h is now exactly the range of f. So here they just swap the domain and the range, because remember we swapped the x and the y, and the range of h is the same as the domain of f, which is R. Easier to understand the definition. The whole purpose of this exercise is to show you the relationship between the logarithmic laws and the exponent laws. So if I look at this graph, the green graph, I see it is a continuous graph. That means that the laws that we previously said, the exponential laws, it holds for first for natural numbers and then for rational numbers. It also holds for real numbers. So the log laws will be similar to that of the exponential laws because they are related. In this exercise, I want to show you the relationship between the two by using exponents to find the logs of 3 different values. This is just an exercise to show you. We will rarely do it in this manner, but it's a good exercise to establish more or less what the value of a log is. In this case, if we look at 600, then I can write it as 10 to the something and 29 and also 0.7. I did 3 examples. I want you to pause after we've done the 600 and try 29 on your own, and then again pause and do 0.7 and then look at the answers. What I also did is I listed numbers 1000 up to or down to 1 over 1000 and wrote it as 10 to the something, where the something is now the exponent, and then this, like 100, can I write as 10 to the 2. Now that 2 there, the 2 there, or the exponent there, is actually the log to the base of 10 of 100. And so is 3 is the log base 10 of 1,000, etc. So this helps us to determine other logs. Now for this exercise, which is a little bit tedious, remember we have the scientific calculators, but the reason for this exercise is for you to understand where does log fit into the whole system, and why do we have certain log rules, logarithmic rules. And if you understand how we get from exponents to logs, then it's very easy to remember all the log rules. My first example that I did is I took the number 600, and if I took the number 600, I will place it there because it's in between 100 and 1,000. That means that the log of 600 should be in between. So log to the base of 10 of 600 should be in between 2 and 3. So let us see how can we find the log of 600 without using the function log on our calculator. Since we know 600 is situated between 100 and 1,000, we can now take, remember the log function is a strictly increasing function, so it means it cannot do something funny in between. So if 100 is less than 600, less than 1,000, then the log of 100 will also be less than the log of 600, less than the log of 1,000. Just taking logs both sides. But log of 100 is 2, so log base 10 of 600 is less than 3. And in this case, let us guess 10 to the power of 2.5 and see what it will give us. I should probably take something a little bit higher than 2.5 because 600 is nearer to 1,000 than to 100. Perhaps we should just start with 2.7, and if we do that on a calculator, we get 501, which is less than 600. It means that we did not estimate high enough. So if we try now 10 to the 2.8, this is just trial and error, and the purpose of this is to show you the relationship between exponents and logs. If I try 2.8, I get approximately 631, which is now larger than 600. So now I can definitely say that the log to the base of 10 of 600 lies in between 2.8 and 2.7. We still do not have the specific answer, but now we can refine it a little bit. So if we try now 10 to the power of 2.75, we get approximately 562, which is still not 600, but 10 to the power of 2.78 will give me 603. So that's more or less 600. So I can say now the log base 10 of 600 is approximately 2.78. If I look up the log, I get log to the base of 10 of 600 is approximately 2.778. And this is now by trial and error. Let us look at a new example. In this case, I will look at 29, and we know that 29 is in between 10 and 100. So in this case, I can start by writing 10 as 10 to the power of 1, and 100 is 10 to the power of 2. That means if I take log everywhere, then I get log of 29 is less than log of 10 squared and greater than log of 10 to the 1, which is just 1. So log of 29 is in between 1 and 2. Since 29 is nearer to 10 than to 100, let us try a smaller number. So let us try 10 to the 1,4. And if you look that up on a calculator, we get approximately 25.12, which is less than 29. If I try something larger, because 25 is near 29, if I try slightly larger, like 1.5, I get approximately 31,62, which is in this case now larger than 29. So now we know that 29, the log to the base of 10 of 29, is in between 1.5 and 1.4. In which case I can now narrow it down a little bit. So let us take something in between. Let us try 10 to the 1,46. Then I get approximately 28,84, which is almost 29. In fact, the log to the base of 10 of 29 is, when we use the calculator to look up the log, we will get 1,462. So we have a very good guess here when we took 1,46. Let us look at the last example where we have log to the base of 10. First of all, we look at 0,7. 1 over 10 is the same as 10 to the minus 1 less than 0,7, and that is 10 to the 0. 1 is 10 to the 0. So if I take logs everywhere, remember, I don't write log base 10, that's the same as log. Then I get log of 0,7 is less than log of 10 to the 0, so minus 1 log 0,7 and 0. If I try something like in between there, then I will get 10 to the minus 0,5, I will get approximately 0,316, which is less than 0,7. So we must try a little bit more. Let us try more in this sense. We must go nearer to 0 and not so near to minus 1. So let us try, for instance, 10 to the minus 0,2. That will give us approximately 0,631, which is still less than 0,7. If I try 10 to the minus 0,1, I will get approximately 1,259, which is now larger than 0,7. So we can narrow down our answer, log to the base of 10 of 0,7, we can narrow down it in between minus 0,1 and minus 0,2. If we now try 10 to the minus 0,15, which is in between that two values, I get approximately 0,708, which is very near to what we want. So in fact, if we look up the log directly, then we get log to the base of 10 of 0,7 is approximately minus 0,155. So our guesses were very near to what we had before.